Yes, so here's the topic, which used to be a key focus in logic and relativity. Was we learnt all this from the Hungarians in the first place, and that's the topic that I've been working with. And it's very incomplete work. We do know something about it, but there are more questions than answers. So let me give you a little bit more of the picture. This is a picture of Minkowski space-time. The dots represent space-time points, and we have a time axis and we have a number of space axes. In this picture there are two, and we can consider this to be a Kripke frame. So you evaluate at a space-time point. The future is the future light cone, which goes up the picture, and the past is the other half of the cone through the point, and it shows you the points which are in the past. And the idea is that here am I at a space-time point. The future points are the ones I can send a signal to at up to the speed of light. And the past ones are the ones that can send a signal to me. And so this is a Kripke frame, and we want to know something about the logic of this frame. Well, actually, I say that this is a Kripke frame, but there are actually some choices to be made. So there are four different possible frames to consider. So the first frame, so we have points in the reals to the power n+1. The last dimension is the time dimension, and the first n dimensions are the space dimensions. And the first relation, which is a reflexive relation, says that you can go from one space-time point to another at no more than the speed of light, and it's reflexive. Okay, and the second one is we don't allow it to be reflexive, we make it irreflexive, but otherwise it's the same. It has a different logic, of course. And there are two others which correspond to slower than light, strictly slower than light. Not allowed to go at the speed of light, but you can go as close as you like to it, and there's a reflexive and an irreflexive version of that. So here we have four Kripke frames over r to the power n+1. And in each case, we are considering a temporal logic. So this is propositional temporal logic. You start with propositions. You can use propositional connectives, and we have the temporal connectives: f at some point in the future, g at all points in the future, p at some point in the past, and h at all points in the past. And I'm going to assume this is familiar. Please interrupt if it's not. But that's the basic. This is the prior temporal logic, and that's the one we're going to consider. And the goal is to find some temporal axioms which are sound and complete over the four-dimensional irreflexive frame. This is the one we actually live in. And so all of the rules about how information is passed in our world, insofar as it's flat space-time, at least locally, this is the logic which tells us about everything to do with that information passing in our world. So it ought to be of some interest. I'm not going to motivate it further than that, but it seems to me clear that it would be good. And I haven't achieved this goal, so let me lower your expectations before we go any further. But we do know something. So first of all, we're going to consider what's the purely modal part. A purely modal part is you can talk about the future, but you can't talk about the past. So you have F and G, but instead of F and G, we normally write diamond and box, and you don't have anything to tell you about the past. In this case, the modal logics are for the reflexive frames are all axiomatized by S4.2, and what that means is that you have an axiom for reflexivity, transitivity, and confluence. And if you've forgotten what those axioms are, I'm going to remind you a little bit later, but this was a result of Rob Goldblatt back in 1980. probably in this direction. This is the last result, a new result about axiomatization of these kind of spaces that there's been. Well, I could be wrong. No, not quite. No, there's some more, which we'll see in a minute. If you look at the, and here we are, in fact, here's a more recent result. If you look at the slower than light irreflexive frames, again, we're looking here with n greater than or equal to 2, so at least one space dimension. This has also been axiomatized by Shipman and Shapirovsky. And the axioms here, we don't have reflexivity, of course, but we do have transitivity. We have seriality and density. We don't have linearity, but we do have confluence. And there's a stronger property than density, which I'll also define soon, called two density, which works for this slower than light case. So there is another axiomatization that we do have. The other key result is for the temporal logic, so far these are only modal logic axiomatizations, is one dimension, so no space dimension at all, just the real numbers, irreflexive, and this is axiomatized by transitivity, seriality, no end. By the way, these axioms, there's one for the future and a whole separate one for the past. I'm going to assume we've got both versions. You might not need both, but let's assume we've got them. So no end of time and no beginning of time either. Density, of course, this is valid. Linearity, it works in this case. And one more, which is the axiom of Dedekind completeness, which I will remind you of. And this was a result of Burgess. That looks like it's a reference to a paper by Burgess and Gurevich, but I think I may have made a mistake here. The original thing is due to Burgess. Anyway, this axiomatization is known. We know a few more things about Minkowski spacetime with at least one space dimension now. We know that the validity problem with one space dimension but slower than light is p-space complete. This is a result, well, the p-space hardness is a result of Shapirovsky, and the fact that it can be solved in p-space is a result of McLean and me. Yeah. And also for the irreflexive up to the speed of light, we know that this is in p-space, and we thought it followed that it was p-space hard, but actually we find that there's a gap in the proof there. It's certainly in p-space, it looks like it's p-space hard, but actually there's a gap in the proof, which I'll say something about in a bit. Similarly for the reflexive cases, with two dimensions, these are decidable. This is a proof that we have, and it's p-space hard. This is a result of Goldblatt, and it follows from Ladner's theorem, which is you can reduce the quantified Boolean formula problem to any logic, any modal logic, which extends K and is extended by S4, transitivity and reflexivity. Now, we proved that they were decidable. We thought, in the line above says that the irreflexive case, we proved that this is p-space. And we thought it followed quite easily that these reflexive ones would also be p-space, because after all, if you have a formula and you want to know if it's satisfiable in reflexive space, just replace future p by either p is true now or p is true in the future. So we can sort of, this is reduction from the, let's get it the right way around, from the irreflexive case to the reflexive case. And it is a reduction, but the problem is that the formulas could become exponentially bigger when you do this. So there is a mistake in our original proof there. It is decidable, it is p-space hard, but we don't know technically that they're in p-space. When you have more than 2 dimensions, so at least 2 space dimensions. They look like they're undecidable, these problems, but the only proof we have is that they are at least x time hard. But beyond that, we don't know, really. Okay, that's the caveat about the mistake in the original papers, let's move on. Okay, I promised to remind you about some of these axioms. So here's the first one, which is called the axiom of reflexivity. This axiom is valid in a frame if and only if the frame is reflexive. Similarly, transitive and dense, these are defining axioms. They're valid in a frame if and only if the frame has the required property. These are also Salkvist formulas, which means that these formulas will be true in the canonical extension. It gives you, it guarantees that these formulas will be complete over various classes that we'll consider later. Here's another one, which is the axiom of linearity. So if you can see P in the future and you can see Q in the future, then one of them comes first, the other one comes either at the same time or later. And that's the axiom there. It's another Salkvist axiom. It defines the class of, well, almost the class of linear frames. Actually, you can take disjoint copies of linear orders and have them running in parallel, and this axiom is still valid. So it's not exactly defining linearity, but it guarantees that each component is linear to the future. Seriality means there's no end of time. Now, we're going to be working in Minkowski spacetime, and if you have at least one space dimension, we're not going to be able to assume linearity. It's going to be false. So instead of linearity, we will have confluence, which is if 2 points are in the future, then they can send a light signal ahead and they'll meet again at some point in the further future. So it's a confluent frame, and so this axiom will be valid. And here's the axiom I promised you earlier, called the 2-density axiom. Imagine that we're going slower than light. If you can see P in the future at slower than light, and you can also see Q at slower than light in the future, then it's possible to go a little tiny bit in the future and still see P and Q. They're still accessible in the future at slower than light. Maybe you have to go a bit faster this time to see them, but they're still just about available. So this is valid if you're considering the irreflexive slower than light frame. But it wouldn't be valid if you were looking at the irreflexive up to the speed of light. Imagine 2 light lines through a point, and along one you can see P, but nowhere else. Along the other you can see Q, but nowhere else. As soon as you go into the future, this is the irreflexive frame, so you go strictly into the future, you could go towards P and still see P, but then you'll no longer be able to see Q. So you won't be able to see both of them. And so this axiom is false, or it fails to be valid in the irreflexive up to and including the speed of light frames. If we have, there's a weaker formula which is below, which is I'm calling 3-2 density. If you have only one space dimension, then there are just 2 light lines through a point. And maybe you can see 3 things in the future, P0, P1 and P2, you can see them all, and maybe they're on different light lines, or maybe they're in between. Well, you can go forward a little bit, and it may be that you can't see all 3 of them anymore, but you will be able to see at least 2 of them. I mean, the worst case, 2 of them lie along one light line, and the other one lies along the other light line. So go along the light line where 2 of them lie, and go not very far, so you're still in, they're still both in the future, and at this point you can still see 2 of them. You lost the other one because it's on the other light line, but you can still see the 2, so you can at least see 2 out of the 3, and this is what I'm calling 3-2 density. And one more axiom, which is the one which is needed to complete the proof of Dedekind, that the axioms are complete over the one-dimensional reals, is the Dedekind completeness axiom, supposing P is true in the future, but eventually it'll never be true again. Then there's a first point where t is never true from here on, strictly in the future, but we don't know whether p is true or not at this particular point, but we know that as soon as you go in the past, there will be points where p is true. There will be later points where p is true. In other words, there's a point in the future, and p is never true from then on, but either at that point or arbitrarily close to that point, there were points where p was true, and this can be used to prove the completeness of transitivity, reflexivity, linearity, Dedekind completeness, sound and complete for the modal logic of the real numbers. Some comments which I have underneath. I pause in case anybody has a question at this point, but nobody does, so let's move on. There's a new piece of notation here. When we're working with irreflexive up to the speed of light, this 2 density can fail. And this notation indicates a failure of that axiom. We'll say that up arrow RS is true if you can see R in the future, you can see S in the future, but as soon as you go forward, you can't see both of them. So this can only happen if R is true along one light line, and not S is true only along the other, a different light line. They're never true on the other light line. R is true on one line, but not the other, and they're never true at less than the speed of light either. So along one line you can see R, but you never see S. Along that line, along the other light line, you can see S, but not R. And at slower than light, off the light lines, you don't see either R or S. So this sort of forces R to be true in the future at the speed of light. Now, if we were to add in modalities, I can see R at exactly the speed of light. These logics become undecidable because you can code up the tiling problem. But we're not quite coding that. We can't express that. What we're coding is, yes, we can see R in the future at the speed of light, but a bit more. We can't see it at less than the speed of light, and it's not on the other light line, and a similar thing for S. So we're coding that you can see them in the speed of light, but the formula states a bit more than that too. And here's a dual form definition for seeing things in the past. One more piece of notation which I will use. Hash P or sharp P means P is not true here or in the future or in the past. If it's true anywhere, it's incomparable to the point, the space-time point where I'm evaluating. Right, some more axioms. When we're looking at irreflexive Minkowski space-time with at least one space dimension, we can't have linearity. It fails because space-time points might neither be, two of them may be unordered. But instead of that, we have a weaker axiom which remains true. If you have this formula, P and hash P, I can see P along one light line at the speed of light. I can see something from which I can't see P at all on the other light line. And most importantly, P is true on the first light line, but not at less than the speed of light and not on the other light line. Given that, what you can say is that the first light line is a linear order. Even though the whole space is not, if you can see along the line where P is in the future, you can see Q and you can also see R along that line, then along that line, either one or the other comes first, or they both happen at the same time. So this weakened form of linearity is true. Similarly, a weakened form of Dedekind completeness is also true. If you have this situation where P can be seen along a light line at the speed of light, but not less, and along that light line, Q is true at some point, but eventually along that light line, there are no more Qs. It's never going to be true again along that light line. Then there must be a point along that light line where there will be no more Q's along the light line, but as soon as you go back, provided you go back the way you came, back to the point where this up arrow formula was true, so if you go back along the light line that you first defined, then Q will be true along this light line. So this will be at the first point, and this is a weakened form of Dedekind completeness, which will be valid. A couple of other axioms which are called grid axioms. If I can see an irreflexive point along one light line and another irreflexive point along another light line, so irreflexive means I can see a formula where a proposition is true but it will never be true again. If that's the case, I want to annotate. Let's see if I can do that. Annotate, remove, annotate. Right. I've got a pen. Oh, yeah, good. Whoops, this is very difficult to draw with a mouse, but here's M0. Oh, it's painful. I won't do any more drawings after this one. And here's another point where M1 is true, and here's the point where we evaluate down here. Then, up here, there should be another point. Whoops. And here we should be able to see down arrow M0, M1. That's the first part of the grid axiom. Let's get rid of that horrible picture. No, keep it. We need it a little bit. The second part of the grid axiom says a bit more, which is if we can, all right, down, up arrow. I should have used a pen, one of these fancy tablet pens, but I didn't arrange that. Very painful. But supposing this line doesn't finish here, it carries on and still FP is true a bit longer. Right. Then the point is here, we have another up arrow formula, and a more complicated grid situation pertains. Ask me about that. Let me get rid of this diagram because it's not nice. How do I do clear orderings? Yeah. Okay, I mentioned those axioms anyway. And I have to click. Oh, I want to stop drawing now. Stop drawing. All right, let's try again. Right. Okay, so some known axiomatizations. If we start with the rational numbers in one dimension and we take the reflexive case, the axioms reflexivity, transitivity, and linearity are sound and complete, and this follows from the fact that these axioms are Sylkvist. It follows that they are true in the canonical frame, and that means you can do a sort of back and forth construction from a countable elementary subframe to the rational numbers, and you will get the required models that you need. And this also works for the one-dimensional rational numbers when it's irreflexive, but we have to add in density and seriality here. And the same axioms also work for the one-dimensional reals in the modal case. That proof isn't quite obvious, but it can be done. If we move on to the two-dimensional case, so we have one space dimension and one time dimension now. Goldblatt proved, as I already mentioned, that the S4 axioms are sound and complete over these reflexive frames, regardless of the number of dimensions, and that's all fine. If you look at the yes, this is modal axioms. Yeah, if you look at these slower than light irreflexive, then the result of Sheckman and Shapirovsky shows that these axioms are sound and complete. We can use the two density axioms. If you look at the two-dimensional irreflexive reals where you go up to the speed of light, and this proof hasn't been written up, I told you this is incomplete work, but I conjecture, let's say, that the axioms of transitivity, confluence, seriality, 3-2 density, and light lines have to be linear. These are all modal axioms, and they may be complete.
Excuse me, sorry for interrupt you. You already exceeded by 5 minutes your time. How much time do you still need?
Maybe I'll wind up now, actually, because I don't like overshooting. So thank you for interrupting. Let me jump ahead a little bit. Let me just say that with the temporal axiomatizations, it's much more difficult. We do have a result of Burgess that for the irreflexive reals, but these axioms don't work for, I have no proof that these axioms definitely are not complete for the one-dimensional reflexive reals frame. And if I won't try to explain, but here's a formula which is satisfiable in transitive linear reflexive frames, but it's not satisfiable in the reals. Basically, there's a gap. It demands two open sets to cover a downward closed open set and an upward closed open set to cover the reals, which can't be done. So we know that these axioms can't be complete. So these cases are tricky. I won't even talk about that at all, but I want to jump ahead to some problems. These are the problems which I want to raise these problems because they are incomplete. And if anybody is at all interested in discussing this further, I ask them to email me and we can talk about these in more detail. But there's some results to pick here. First of all, find some sound and complete modal axioms just for the reflexive reals. It ought to be easy. This should have been done long ago, but I haven't found it. Maybe somebody knows a result here. But then we come on to these Minkowski spacetimes. We don't have sound and complete temporal axioms for any frames at all with at least one space dimension. So let's try to find some, have some ideas of some axioms, but we don't have a complete proof. I mentioned that we don't have even undecidability. We haven't proved this for higher dimensional frames. And a really interesting one is what happens when you have curved spacetimes. And one axiom that you will definitely need to drop is the axiom of confluence. If you have two black holes, then you can send a light signal to either of these black holes, but there'll be no confluence because they don't have a common future. So the question is, for various types of curved space-time with various types of black holes, what are the validities, temporal validities that you keep, and maybe even some sound and complete. This is getting ambitious, but that would be something which would be nice to prove. So I've overshot my time. I'm happy to take any questions, but I do urge if anybody wants to study this stuff and wants to talk about it further, just contact me and we'll talk about it in greater detail. Thank you.